Our language, the primary way for normal, sane human beings to communicate. This being the case, a good human language should be easy to use and remember, and allow for any idea to be communicated easily and efficiently. There's only one issue with normal human languages, which is that they have a lot of words and rules. The most egregious example of this is English, with 170,000 words. It really would be easier if someone made a language with as few words as possible. One of the most famous examples of this is Sonia Lang's language, Tokipona, which, for those unaware, is a Conlang that she made to be simplistic and elegant, and it does a good job with fewer than 200 words. It does require a little interpretation, but that's to be expected of such a small vocabulary, so long as one wants the language to remain remotely usable by human beings. But what if we didn't want our language to be usable by human beings? What if our only goal was to minimize the amount of words we would need to define, while making sure that all statements could not possibly be misinterpreted? Well, for the sake of interest, I've done just that, and the resultant Conlang is, without a doubt, the worst communication method I've ever had the displeasure of using. Today, I'm going to explain it, and maybe we'll learn a little something about particle physics and set theory along the way. Okay, so this is the language of Bulutabawase. After much deliberation, I landed on exactly 21 words or symbols that could be used to describe almost everything in the universe. Let's meet them all very quickly. I've included some logical operators, namely and, or, and not, which are respectively pronounced you, ru, and nu, and written like this. We also have equals, su, and open and close brackets, bi and bu. I've also added a way to custom define your very own functions with la, a way to create and name custom variables with wo, a way to repeat something a given number of times or until a certain condition is met with ri, and the handy wu, which means do the previous thing only if the following thing is true. Now that we've gotten those out of the way, we can get to the actual things that are things, starting with the most thingish thing of them all, ta, which can refer to literally anything ever. We also have se, which refers to a set of things. A set is merely a collection of any group of things. I could, for example, have a set of a cat, the number 37, and the planet Jupiter. One can individually label things and sets by putting brackets directly in front of them and then some identifying numbers inside. To go with these sets, we have ka, which is for when a set contains a thing, wa, which is for when a thing is in a set, si, which is for getting the size of a set, and ne, which is for getting the nth object in a set. Along with all those is the more broadly applicable lu, which simply gets all the things within any defined boundaries. Finally, we can get to the symbols which are used to define and differentiate actual real-world things. There are only 4 of them, and I'll go through them very quickly. They're called ma, za, pa, and lo, and define mass, electric charge, spin, and position in time and space, respectively. I know all these seem really random, but I promise they are all necessary. Since I don't want to do anything too crazy, let's make the goal of this entire video to talk about a single carbon atom. Sounds easy enough. There is just one tiny problem though, which some of you might have picked up on already, which is that we don't have any numbers at all. Not only that, but we don't have any mathematical operators like addition. So our first challenge is to rebuild all those slightly handy concepts from the ground up. Strap in. The very first of many, many phrases that we will need to make is lu te, which simply means all things. The set that contains all things is a very handy set, but we want to make the set that does not contain all things. This is an empty set because it does not contain anything at all. The size of this set is what we call 0. Let's try to make 1. 1 is the size of a set 2. It's the set that contains just one thing, which we'll specify by identifying it with a 0, and does not contain anything else. So we say it does not contain something that is not 0. It might be a little bit long, but it's still pretty cool. 2 then can be written as the set that contains 1 and 0, and does not contain anything that is not 1 or 0. This is getting a little bit absurd to write. It might be worth defining a function to grow the size of a set by 1, so we don't have to do it manually every time. Here's one way we could do it. Make a new function and call it lambda with an index of 0. We need this index number so that whenever we need to, we can use this particular function. It should take one input, which we will call x0. And we will need to make sure that it is a set. We'll want the output to be equal to a set that contains everything in the input set plus the size of the input set, and does not contain anything else. This might seem like a bit of a waste, but now we can grow numbers more consistently. 3, which used to be written like this, is now condensed down to just this. To define a carbon atom though, we're going to need some more complex mathematical operations, so let's start by making a plus. Addition is just the action of repeatedly adding 1, so here is how an addition function might work. Take 2 number inputs, turn the first input into a set that has the size of the first number input. Then we want to continually repeat our +1 lambda 0 function on the first input a number of times equal to the second input. This will give us a set which has a size of the combined inputs. Then we simply make that the output. We can already do everything within that function except for turn a number into a set. So we're going to need to make a function to do that before we can make our addition function. Fortunately, this is not too hard. Define another function. This one we'll call lambda 1. It should take a single input, which needs to be a number. We then define a new set, which we call set0, inside of this function, which should start as equal to the empty set. We can then use the lambda 0 function to increment the size of set 0 by 1, and we need to repeat this a number of times equal to the size of the input. As a quick aside, some of you might think it a little bit strange that we're choosing to represent numbers as the sizes of given sets, but it does make sense when you think about it. Whenever we say 3, we're really talking about a group of 3 things, like 3 loaves of garlic bread, or 3 ace of spades playing cards. These sets just make it much more apparent. Anyhow, let's finally build our addition function. Define function lambda 2. It takes 2 inputs called x0 and x1, both of which need to be sizes of sets or numbers. We define a new set called s0, which is the set form of x0. It's our first input fed through the lambda 1 function. We then repeat the lambda 0 function on s0 a number of times equal to x1, which is our second input. After all this is done, our output is equal to the size of s0. This entire function, accompanied with the 2 smaller functions within it, is how to write plus in this language. We could have made this its own defined word and saved over 200 symbols of bother. Instead, we've saved ourselves from needing to define 1 extra word. Let's continue on to make some more complex operations. Just like how we defined addition as repeated increments of 1, we can define multiplication as repeated addition. make a new function called lambda3. It should take two inputs, call them x0 and x1, which should both need to be numbers. Then we make a new variable called x2 within the function, which starts as the same as our input, and set the output to the addition function of x0 and x2 repeated x1 times. Or to put it more simply, add input 0 to itself the number of times equal to input 1. Let's round this off by making exponents. You know the drill by now. We can call it lambda 16 because 16 is an exponenty number. Lambda 16 takes two inputs, which need to be numbers. Make a new variable, repeat multiplication of that variable and the first number a number of times equal to the second number. Cool, that wasn't too hard. Next, let's have a look and see if we can make negative numbers, which also means subtraction. We already have a rudimentary form of subtraction by simply removing items from a set, but it doesn't let us go below 0. Of course, we can't actually make a set with a size smaller than 0, but we can pretend that we can. It's just like how negative numbers in the real world don't actually exist, but they can be very useful if we pretend that they do. We can define a new number, which is written as the thing that is the size of a set, where this number plus 1 equals 0. The size of this set must be -1 because the size of it plus 1 is equal to 0. We can make a new function if we like, which we can call lambda -1, which will turn a positive number into a negative number or vice versa. It takes one number called x0 as an input. We make a variable called x1. Our output equals this number, x1, when the input x0 plus x1 is equal to 0. Adding this output number is equivalent to subtracting by the input number. Let's quickly compile that into a subtraction function. Lambda -2 takes two inputs and outputs, and is literally just a copy of the addition function, but with the second input fed through lambda -1 before it gets added. We can make divisions through a similar process. Let's try to make 1/2 first. 1/2 is the number that, when multiplied by 2, equals 1. So let's write that. The thing that equals 1 when applied through lambda 3 function of 2. That sounds a bit scary, but all we're really saying is the number that when multiplied by 2 is equal to 1. Remember that, even though this number is expressed as the size of some set, the set which represents it is completely imaginary. You could never actually get a set with a size of 1/2. Let's make a more general division function. Lambda 1/2 takes two number inputs and returns the number that, when it is multiplied by the second input, equals the first input. Could keep going if we wanted to, rebuilding all sorts of fancy things like sine and cosine, or tetration, or square roots, but we don't need to for the moment. If you'd like to have a go though, I'd be more than happy to see what you come up with. Now we can finally get on to the actual particle physics bit. A carbon atom is represented by its component parts in this language. A standard atom of carbon is made of 6 protons, 6 neutrons, and 6 electrons. Each proton and neutron is made of quarks, with 2 up quarks and 1 down quark for a proton, and 2 down quarks and 1 up quark for a neutron. Electrons are fundamental particles on their own, so they can't really be subdivided. Let's start with them. First, we need a way to talk about a particle, which we do like this. A particle is simply a thing that does not contain all things that are not itself. That might sound a bit confusing, so let's break it down. All we're really saying is that the thing cannot be reduced into more pieces. Its set of components does not contain anything except for itself. We can represent an electron as one of these particles, but that meets specific conditions. First, we can define the mass. The mass of an electron is about 0.0000000000000009 micrograms, which is approximately 4.1 times 10 to the negative 23 Planck masses. Let's express that using our notation. Since that won't fit on the screen though, I'm just going to write that using our standard base 10 notation. But rest assured that all the numbers I'm about to use could be represented in this Conlang. Next, we need to input the other characteristics of an electron. The charge of an electron is the charge of one proton multiplied by -1, or -1e, where e stands for the unit of one elementary charge. Let's write that down. Lastly, electrons have a spin of 1/2, which we can note down too. We don't need to worry about the position of this electron, since there aren't any other particles to compare it to. Let's define a function to talk about electrons called lambda4, just to make it so we don't have to rewrite this out every time we want to mention one, which we're going to have to do 6 separate times. Next, let's make a function for an up quark and another for a down quark, lambda5 and lambda6. We humans actually don't know the mass of up or down quarks for certain, but we do know that they're both very, very light. A true speaker of this language would know the mass exactly, but for us feeble humans, a simple question mark will have to suffice. Up quarks have an electric charge of exactly 2/3e, and down quarks have a charge of -1/3e. Down quarks and up quarks both have a spin of 1/2 too. To build a proton and neutron, simply combine 2 of one type of quark with 1 of the other, and define their exact distance apart. The strong nuclear force makes this distance very hard to measure, because quarks hate being on their own, but we can assume that they're very close together indeed. Call a proton lambda7 and a neutron lambda8. Clump 6 protons and 6 neutrons together with a distance of about 10 to the -15 meters, around 62 quintillion 500 quadrillion Planck lengths apart. Then add 6 electrons, which orbit the nucleus at a whopping 0.0000000005 meters, or about 6.25 sextillion Planck lengths, though the exact distances vary from electron to electron, especially in a carbon atom where there are multiple occupying more complex orbits. And there you have it, a carbon atom in all its glory. Here, for those interested, is the complete description. It also has a spoken form, but I'm not even going to try to attempt to say it because it would likely take several hours to pronounce. Well, that sure was an adventure. Was it a huge waste of time? Probably. But did we learn something interesting? Well, I hope so. If the universe spoke, it would speak in a language a little bit like this. Convoluted, utterly incomprehensible, and not for human use, but logical behind all the madness, and very pretty in a strange way.